Have you ever just looked around and wondered about the stuff that makes up our world? I mean, really looked. From the toys you might have played with as a kid to the very screen you're looking at right now, it is all made of these incredible engineered materials. Today, we're going to peel back the curtain and look at the hidden science that makes all these everyday objects, well, possible.
All right, let's kick things off with a question for you. What on earth do Lego bricks and those old, super heavy, black rotary telephones have in common? They seem like they're from different planets, right? But the answer connects them, and it takes us right into the amazing world of polymers. And that's exactly where we're going to start.
So, we all think we know what plastic is, but it turns out plastic is this huge family of materials. And the key difference, the thing that really separates them, is how they react to heat. It basically sorts them into two completely different camps.
Okay, so on one side, you have thermoplastics. Think of these like a candle. You can melt a candle down, let it cool, and then melt it again. You can reshape it over and over. But on the other side, you've got thermosetting polymers. These are a whole different story. They're more like baking a cake. Once you've baked it, that's it. The change is permanent. You can't unbake a cake, right?
Now this is where it gets really interesting because this shows us why they're so different. Our Lego bricks, they're made of ABS, which is a thermoplastic. Its molecules are kind of like long strands of spaghetti, just loosely tangled together. So when you heat them up, they can slide past each other, which means you can melt them and recycle them. But that old Bakelite phone, that's a thermoset. Its molecules are locked into the super rigid 3D web. Try to heat that up and it's not going to soften, it's just going to char and burn.
All right, so we think of plastics as insulators. That's why we wrap electrical wires in them, right? To keep us safe. But what if I told you we can actually make some plastics conduct electricity? Yeah, this is where material science starts to feel a little bit like magic, and it's opening up possibilities for stuff like flexible screens and electronics you can literally wear.
The secret ingredient is all in the molecular structure. See, certain polymers, like this one called polyacetylene, have a backbone that's a special pattern of alternating single and double bonds. This pattern creates a sort of potential highway for electrons to move down, but it needs a little push to really get things flowing. And that push is a process called doping. And no, it's not what you're thinking. In chemistry and material science, doping just means you add a teeny tiny amount of something else, an impurity, to change how the material behaves. It's the secret ingredient that unlocks that conductivity and turns our plastic from an insulator into a conductor.
So here's how it works. You take your polyacetylene chain, and you introduce a dopant, like a little bit of iodine vapor. Now, iodine is really electron hungry, so it literally snatches an electron away from the polymer chain. This leaves behind what scientists call a positively charged hole. Now, it's not actual empty space. It's just a spot where an electron should be. And this hole can jump from atom to atom, moving along the chain just like an electron would. And what do we call a flow of charge? An electric current. It's that simple.
So we've seen how just tweaking a material's chemistry can completely change its properties. But what happens if we don't change what it's made of, but we change its size? To find out, we have to go smaller. Way, way smaller. We're diving into the fascinating and frankly weird world of the nanoscale, where the rules of physics as we know them start to get a little bent.
Let me ask you a really simple question. What color is gold? It's gold, right? That shiny, metallic yellow that we all know. But what if I told you that gold can also be red, or green, or even orange? It all comes down to how big the individual particles are.
And just look at this. This shows you just how different things get. When you shrink gold down to the nanoscale, it's like it becomes a totally new material. The color is just the beginning. Bulk gold is one of the best conductors there is. Nanogold is a semiconductor. Bulk gold is super inert and unreactive. Nanogold is an amazing catalyst, which is why it's used in everything from medical tests to controlling pollution. The entire identity of the material just shifts.
So, why the color change? Well, a big piece of gold just reflects yellow light back at your eyes. Simple enough. But nanoparticles are so incredibly small that they interact with light waves in a totally bizarre way. They cause electrons on their surface to oscillate. It's a phenomenon called surface plasmon resonance, and this scatters light instead of just reflecting it. And the color they scatter depends on their exact size. 25 nanometer particles look red, 50 nanometer particles look green, and so on. Wild, right?
Being able to control properties like this is, well, it's revolutionary. But if these nanomaterials are so incredible, how do you actually make them? How do you build something on a scale that's 1,000 times smaller than a single human hair? It turns out there are two very different ways to think about it.
So there are two main philosophies here. First is the top-down approach. This is basically being a sculptor. You start with a big block of material, and you just carve and etch and chip away everything you don't need until you're left with your tiny structure. Then there's the bottom-up approach, which is the complete opposite. This is like building with Legos. You start with the smallest possible pieces, individual atoms and molecules, and you precisely assemble them into the exact structure you want.
And just to keep the scale here fresh in our minds, we are talking about structures between 1 and 100 nanometers. A single nanometer is a millionth of a millimeter. That's the tiny, tiny playground where scientists are literally building the future. The Sol Gel process is a perfect example of that bottom-up, Lego-style method. You can think of it like a recipe. First, you mix your precursor chemicals in a liquid. That's your Sol. Then, through some cool chemistry, these precursors start linking up, forming a rigid jelly-like network. That's your gel. After you let it age, dry it out, and heat it up, you're left with a super pure, perfectly uniform nanomaterial that you've built right from the molecule up.
You know, this quote right here really gets to the absolute heart of everything we've talked about today. When you get down to the nanoscale, you're not just dealing with the classical rules of how materials should work. You're entering the world of atomic physics, where the rules are just different, and the possibilities become almost limitless.
So from a simple plastic brick to particles of gold that shine bright red, we've seen that controlling matter at the molecular and atomic level changes everything. And it leaves us with this one huge, fascinating question. Now that we can engineer materials literally atom by atom, what are we going to create next? What problems are we going to solve? The future is being built as we speak, one atom at a time.